Hello everyone. So we're going to move into the last section of Unit 1. So now we discuss about electric force and electric field. So this section we're going to discuss about the uh, electric potential, because you know that how useful energy is in your physics 1 class. So energy is conserved quantity and very important tools to understand the nature and solve the problems easily. So now in electricity, we also going to use the energy concepts to solve the problem. Because of that, we're going to talk about uh, practical devices, capacitors that store the energy for later use. And you know that capacitor has a camera flash or energy backup devices like computers. We have those as using the capacitors to store the energy. So electric circuits are basis of the many devices that we use in the society. Circuit elements can be connected with the wires from electric circuit. Capacitors are one of the circuit, one of the device element that we're going to discuss in this chapter, but there are more to come, like resistors and power supplies and those things later on the semester. Okay, so now in this chapter, we're going to talk about basically electric potential and the potential energy. So that's the part that we're going to cover in this chapter. Okay, so now let's move into the your blackboard page first a little bit. Share it. Okay, so we're going to work with the chapter 19. That will be the last section of your unit 1. Okay, so this will be a little longer chapter that we need to talk about electric potential, potential energy, and also capacitors at the end. Okay, so now let's move into the slides. Okay, so now first thing is electric potential. So electric potential at your point of interest point will be able to calculate by using work done principle that we talk in your physics 1 class. That means if you have a source charge, if your point of interest in here, if you bring a charge from very, very far away distance, that will be infinitely far away distance, you're going to bring that charge particle to your point of interest, then how much work you have to do per this charge, we call it as the electric potential. One more time, if you need to bring this particle far away, infinity long distance, to your point of interest, then how much work you have to do bring this charge particle to this point, we call it as the per unit charge, we call it as the electric potential. Electric potential is basically work done divided by the charge. So now work done measured by joules, charge will be coulombs, joules per coulomb, we call it as the volt. Joule per coulomb, we call it as the volt. Joule per coulomb is volt, right? That's the units of the electric potential. Okay, so now it's misunderstanding some student can have. Electric potential is not potential energy. Potential energy is something that I'm going to discuss in a minute, but this is the electric potential measured by volt, not by joules. Potential energy is the energy that you can measure by using joules. That is the work done basically. Okay, but here we are talking about the work done per unit charge. That is the voltage. Okay, so now voltage is very simple thing, because voltage does not have a direction, because it is a scalar quantity measured by using volt, right? So, but this electric potential and electric field are related to each other, because work done is force per unit time, then force will be able to write by using Q and E. Then if you take the change of voltage divided by distance, that will give you the E, right? So now we know the E divided by X will give you the voltage, right? So now what we have, you remember that the force was depend on Coulomb constant, source charge Q and the R is square, then electric field was depend only for the source charge. And when you come to the voltage, now I am saying this should be times the distance, that will give you K Q over R. That is, first two are vectors, but last one is a scalar quantity. Okay, so that means voltage or potential of this object is depend on this source charge, right? That's same for electric field and potential. Only electric force depend on both charges. Okay, so now we have those idea in our mind. So now conservation of energy. So conservation of energy principle is very important. Because of that, we need to think about the conservation of energy principle in here, especially potential energy when you have a charge particle. If that charge particle move in, that has the kinetic energy too. So now let's focus into electric potential a little more. So electric potential is basically potential energy per unit charge or work done per unit charge. Okay, so that is a scalar quantity since energy is scale. Okay, so now when you come to the laboratory, we are not measuring electric potential, we are measuring the potential difference. Why is that? Electric potential difference is the potential from one point to another point. In your voltmeter, multimeter, you have two terminals. One is COM, other one is volt. So if you use COM and volt, that means you are measuring potential difference, not the potential. You cannot measure the potential at one point by using voltmeter, because there should be two terminals to measure it. That will be the potential difference that you are measuring. Okay, so now let's analyze this problem a little more for you to understand the work done principle that work for your physics 2 class. Work done is force time distance. We know how to calculate it. In this case, it will be electric force times distance. So now I have a problem. So there is a particle, positive charge, moving from, in this case, right to left, and electric field is left to right. So now my first question is, electric field, which way will be the electric field? So now everybody know that since electric field left to right, then you have the terminal, positive terminal in this side and negative terminal in that side. I have a bigger picture in here, but vertical direction. Positive side will be here because electric field start with the positive charge. Okay, so that will be the diagram that I need for the analysis. So my first question is, A, electric field. Okay, so it's asking, is positive or negative work done? That's the question. Is positive or negative work done by electric field? That's the A. Now, electric field has the direction of moving of particle to the opposite direction. Remember that work done is force times distance. We discussed that in your physics 1 class. Force and distance. In this case, it is electric field and distance. But if force and distance are in opposite direction, your work done is negative. So now my first question is, electric field do a negative work done because they two are opposite direction. I hope everybody understand that. Negative work done. Okay. My second question is our force, not the electric force. Electric force on this particle will be, again, do the negative work. But what you are doing, you try to push this particle in this way by applying the force opposed to the electric force, right? Electric force in this case will be this direction. This is the electric force direction. But you're going to apply the force in opposite direction to move the particle into the positive terminal. Then that applied force do positive work done because moving in the same direction. Then B will be positive work done. Okay, now let's move into the C. Does the electric potential energy increase or decrease? Electric potential energy moving from here to here increase because you're going to move into the high voltage. So it will increase. And last question is, does the proton move to a higher potential or the lower potential? Definitely it will move to the higher potential. Higher potential, because it moves into the high voltage position. Okay, so now this is understanding about what the electric field do, what you do, what where is the positive terminal, where is the negative terminal, what directions your proton will move if you apply the electric force or electric field into that direction. Okay, so now equipotential surfaces and electric field lines. So now in your theory class, we learn about electric force, we learn about electric field. Now we are learning electric potential. But when you go to the laboratory, you do not have chance to learn electric force and electric field, because in the laboratory, you are not able to measure those things. Only thing you can measure is current and voltage, right? After you measure the voltage, you will be able to realize the electric field by doing backward method, right? That's what the laboratory do. So now, equipotential means basically potential constant line, we call it as equipotential line. If it is a line, that will be equipotential line. If it is the surface, that will be equipotential surface. If it is the volume, that will be equipotential volume, right? Depend on your shape of the object. So now in this case, we have potential line. If you create a positive terminal and negative terminal in the laboratory, you're going to give the negative terminal and positive terminal. Now, if I measure the voltage in these points, this line that I have here, all the way this line, I will get the 15 voltage. That is, we call it as equipotential line, because everywhere in that line has 15 voltage. So now if you go to the center, if you measure this line, this green line, you're going to see everywhere is 10 volt. If you go this line, you're going to see everywhere is 5 volt. Those we call it as equipotential lines. My blue, the green lines in here. So after you draw your equipotential lines, then you will be able to draw the electric field lines, because electric field lines is starting from positive, ending with negative, but these all connections I have will be perpendicular to equipotential lines that you need to follow when you do backward drawing. Okay, so now similarly, you have positive and negative terminals, you can do the exactly same. You see that you have symmetrical kind of eyeballs that we have the equipotential lines. Those are equipotential lines. Okay, so now again, your electric field lines can draw after you draw the equipotential lines as a perpendicular lines with the direction starting from positive and ending with negative charge. Those will be electric field lines. Okay, so now it's very important that equipotential lines means equal potential. Then you go to the potential difference, work done per unit charge. That means basically there is no work done if you need to move a particle on the equipotential line. That means if you need to move a particle from here to here, no work done needed, because that is equipotential line. Potential is the same. Okay, no work done. And so now sometimes student will confuse with electron volt and volt. That's why I have this definition in here. Electron volt is not volt. Electron volt is joules. One electron volt is equal to this much of joules. Okay, so that's the definition of the electron volt. It is not the volt. It is the energy gained by an electron moving from potential difference of 1 volt. We call it as the electron volt. Okay, as I mentioned, your equipotentials can be surface, can be volume. In this case, I have the surface 1, 3, 4, and 2 that you can understand the path. Basically, if this is a equipotential line, path 1, you move exactly on the same plate with the equipotential surface. That means you don't do any work done, right? But if you go to another place and come back exactly the same plate again, still there is no work done, because it is this work done for the electric force is conservative force. Because of that, it has work done is independent of the path that you learn in your physics 1 again. So conservative forces means you have work done is independent of the path. Those those is the one of the force is the electric force, or gravity is the other one. You discuss in your physics 1 class. So still no work done. But if you go from one plate to second plate, if they are sitting in different potential, as I have V1 and V2, then you have to do the work done. Okay. And here also you go somewhere and come back. It doesn't matter where you go. Important thing is starting and ending point for the work done for electric work, electric potential work done. Okay. So because it is independent of the path. Okay, I think you have some kind of idea. So now let's move into this question. So I have equipotential lines 90, 80, 70, 60, 50, and 40. And I have path taken 1, 2, 3, 4, and 5. So now it says that 5 path alone, electron is the particle that will move. And what is the direction of electric field associated with the surface? Now, as soon as you see the equipotential lines, you know that this terminal is positive terminal and this terminal is negative terminal. That means my electric field will be starting from positive, ending with negative. That will be the answer. Okay. Okay, that is A. Then B, for each path is the work we do positive, negative, or zero, right? So now we do means you're going to bring the particle negative charge from your path 1. So now in path 1, it's a little up that I can see the screen. So you're going to move the particle in path 1. That means you're going to start with 80 volt and you're going to end up with 70 volt. Your voltage difference is 10, and then your work done will be basically potential difference times the charge. So now potential difference finally is 70, initially is 80, then 70 minus 80, you're going to divide by the negative charge. That will give you a work done. Okay, so now you go to the second and do the work done. There is no difference between 1 and 2. Your work done is still the same because the initial and ending are the same. And then you go to the number 3, your work done will be greater. And number 4, you have work done but in opposite direction. And then I have 5, work done will be same as 1 and 2. That will be the same direction. So now by analyzing of the work done that you can see, you will see that your work done in first case is a positive work done because you bring in particle from 80 to 70, but it is a negative particle. Because of that, you do the work done as positive. And then 2 also positive, 3 also positive, but it is greater, and 4 is negative work done, and 5 is doing positive work done. Okay, so now rank the path. We know that 1, 2, and 5 are the same work done, but 1, 2, and 5 are the same work done, and also 4 has the same work done, but it is negative direction. 3 is the most work done. Okay, so that will be the work done of the all of those. Okay, try to think in your head one more time about the work done and get an understanding about how that will work. Okay, so now electric field has the relation to your electric potential. As in the example, if you do in the laboratory, if you measure the electric potential in this place and this place, if you know the electric potential, you can take the potential difference, divide by the distance between these two lines, then that will give you the electric field. That's how you're going to calculate the electric field in the laboratory. Okay, so that will be delta V divided by delta X, but there is a negative sign in front of that. So that will give you basically the negative value of the electric field according to the potential difference. So that will give you the electric field, and also potential per point charge. We already discussed that will be KQ over R. Okay, so now how this electric potential behave with the charges? As I mentioned earlier, electric potential is a scalar quantity, but it can be a positive or negative depend on your discharge. If this charge is negative, your potential will be this way, right? If it is a positive charge, your potential will be 1 over R relation. That's how the potential change. That means if it is a negative charge, your potential is negative. If it is a positive charge, that will be positive potential. Okay. Okay, so now potential from many charges. You can calculate the potential by using many charges, right? If I need to find the potential at this point, I may have a lot of charges around that. Then I need to add all the charges to my potential formula with the distance. That will give me, this is your Coulomb constant times Qi over Ri. Qi is the charge of the source charge. Distance between your point of interest to that source charge is Ri. And then you go to the second one, do the same, third one, do the same, add them all. That is what this summation means. And then you're going to end up with your total potential. That means your total potential, you're going to add Coulomb constant, your Q first source charge, distance to that, and plus K second source charge, distance to that, and keep adding the terms. That's what the summation means. Okay. So now, in addition to that, according to this formula, you will see when R goes to infinity, 1 over infinity means potential is 0. That means my potential 0 point is infinitely long distance, but I can have positive and negative potential according to the charges that I have it in source. Okay, so now I have this example on the bottom. I want you to understand how do you find the potential due to your point of interest due to two protons that I have. I have one proton here, another proton here, and my point of interest is this place. Now, if I calculate the potential in this point, I know that that will be K, charge of the proton. I'm going to say Q, and distance to first one is D, and plus K, charge of the proton, same charge, and distance is D, right? If I do the same for B and C, do you see any difference? You don't see any difference because your two charges is staying with respect to your point of interest. Distance D and uppercase D, they are the same charge. Then your formula will be the same for A, B, and C. So your answer is the same for all. Okay, that kind of potential. Okay, so now we're going to move into the potential energy. So as I mentioned, potential energy per unit charge is the electric potential, right? Potential and potential energy are related, but calculating potential energy, you need to do another process that will give you all the combination of the charges you need to do. As a simple example, if I have two charges, you need these two charges, and also you need the distance. That is called it as the potential energy, right? If I have another two charges in this system, somewhere here and somewhere here, then what you need to do is you need to take this pair, also you need to add, if it is Q3 and Q4, then you need to add with the distance D, you need to add the K, Q3, Q4, and distance D. And in addition to that, you need to keep adding each pair to the system. That means in this example, it is not done yet. You need to take this pair, right? And also you need to take this pair and this one, and also this one. You need to keep adding the terms until you complete your whole pairs in the diagram. Two charges together always. How many two charges I have together here will be, you need to have 5 terms in here basically. Okay. So, I mean, 6 terms in here. So you need to do adding of these 6 terms, a lot of work of calculating potential energy. Okay, so applications, Van de Graaff generator, I talked about that earlier section also. Watch the demonstration about the Van de Graaff generator because this is a very important application of the your charges, that how you project or how you create the metal dome with the charges by using traveling or distribution of the charges. And Millikan oil experiment is another experiment that you can observe that will basically measure the E of the elementary charge of electron basically what it does is you have two plates and you have a pinhole here. Then if you draw the oil droplets and if you light it up, you can observe from here what will happen to this charge particle, right? So simple example, if I have a negative charge in the middle, what will happen is this negative charge will have a force of gravity and there will be a drag force because of the resistance in there. And then it will, when they equal and opposite, it will create a terminal velocity as we discussed in physics 1 class. Then that charge will travel in with terminal velocity, right? So now what the important thing in here, since this two plate is connect into electric field or electricity, then these two plates going to be charged. Because of that, there is an electric force happening in this charge. Now this charge has the electric force. Now you have the drag force and mg, but if electric force and two drag forces are equal to each other, then there is a terminal velocity that object will reach the or stick into the top plate. So according to where it go, you can decide, you can measure the magnitude or the charge of that particle. So that is called it as Millikan oil drop experiment. Okay. And also next step is learning about the capacitance. So capacitance basically store the energy. This is the first device that we're going to learn in your class. Capacitor will use to store the energy for later use. That's what it do, right? Store energy means basically storing charges. So now capacitors, this will be real life capacitors that you can have inside your computer and so on. And but capacitor can have cylindrical shape, can have spherical shape, can have parallel plate capacitor. This is what we're going to study in your class, but there are many other different shapes of the capacitor, but purpose is still store energy on the capacitor or store charges on the capacitor to use it later. That's the idea about the capacitors. Okay. So now parallel plate capacitor symbol for the capacitors, we use this same length two lines, and this will be the symbol for the battery, right? So now capacitor has the letter C that we call it as capacitance. Capacitance is the value of the capacitor. Capacitor is the device. Capacitance is the value of the capacitor, right? That value, that C number, you cannot change it. C is manufactured number that will be defined by the manufacturing process by changing some variables in the capacitor. But the main equation for the capacitor will be charge equal capacitance times the voltage you're going to apply. So now as soon as you see in here, C will be Q divided by V. Q is coulombs, V we're going to measure by volt. Coulomb over volt, we called it as farad. Farad will be the unit of the capacitance. Okay. So capacitance is always a positive value. It is constant for given capacitor. It is not able to change. Only thing you can change is the voltage and the charges that you're going to change. According to that ratio, your capacitor will keep constant. So now the capacitance, more capacitance means you can hold more charges. That means you can store more charges. Okay. So now the capacitor, I have a lot of derivations in here, but you don't want any of those. You can do it for fun if you want to do. But now idea is this capacitor, when you have two plates, so that has the electric field that we calculated earlier, that electric field here is equal to the charge density divided by epsilon naught that we discussed earlier. By using those informations and by using voltage information to the electric field, this information you can easily derive this equation. Okay, so this is the manufactured C value that is depend on epsilon naught. That means the material that you're going to use in between these two plates, and A is the cross-sectional area of those plates, and D is the distance between these two plates. right? What this means is if you have more cross-sectional area, capacitance going to increase. If you have less distance very close to each other, then you have capacitance is greater. That can be changed by using those parameters. So now I also have the different formulas for cylindrical capacitor and spherical capacitor. If you want to try with those formulas, how it will change and those things. Okay, but we're going to focus into parallel plate capacitor in your class. So now C equal epsilon naught A over D, as we discussed. Epsilon naught is permittivity, that well-known number that we already know. But you see very important information. This in between these two plates, you should have a material. If it is the air, then you have epsilon naught only. But if you have different dielectric media in between these two plates, so then you're going to see your dielectric constant come up to your formula. That is, we call it as the final formula. K is dielectric constant. Dielectric constant is always greater than 1. Okay, because it is the ratio of the permittivity of the media divided by the permittivity of the air. So this number is always greater than 1. Okay. Okay, so now dielectric media a little bit. Dielectric means basically insulator. So if I have an insulator in between these two plates, what is actually happening is insulator cannot carry the charges. So now how do you going to charge this? So insulator, when I have insulating media, these charges going to basically stay in together. There is no way you can separate those charges inside the insulator, non-conducting media. So now, because of this charge separation or charge polarization, they will create a small electric field that I have it in this blue color. That is creation because of these dipoles that have positive and negative. Then, but I have electric field created in between plates. Then you know that this blue color E is much smaller than the E naught I have. If you take the ratio of E naught to E, that will again give you the dielectric constant. Earlier I mentioned that this will be epsilon over epsilon naught. That will be basically permittivity information. This is electric field information. Those will be the give you the same answer. Okay. And I mentioned capacitor will store the energy. How much it's going to store? So energy stored in the capacitor, we call it as the, I'm going to write E in here, that will be QV divided by 2. So now this is one way that you can write, and then you can use the capacitance formula. You remember that capacitance, we have Q equal capacitance times voltage. I can plug voltage into here. Then I will be able to write this as, if I want, Q squared over 2C, and also I can write it as half CV squared. So I will use the E because it is the energy or the work done. You can use W or E. They are the same thing. They are basically energy stored on the capacitor. Whichever equation you can use it. These three formulas are the same. Okay, my last part about the capacitor circuits little bit. So we will come back to this series and parallel connection more detail in your resistor part. But here I need to finish with the capacitor. That's why I included that into here. So now capacitors can be connected in series, in parallel, or combination of both. So now here I am showing you have capacitor C1, C2, and C3 are connected parallel. Parallel means you're going to connect one by one on the parallel lines. What that means is basically they have different charges on each capacitor. Each capacitor has different charges because they have different wires. This one has one wire, this one has different wires. Because of that, they have different charges. According to that, you can define this circuit, that voltage I have it on this circuit. You're going to have the same voltage because this is the two terminals connecting to your power supply. That means voltage between these two terminals, these two or these two going to be the same, but they have different charges. So now this is, we call it as the parallel capacitors. If you have parallel capacitors, you can combine these three together, 3 or 4, any number of capacitors, by using the formula that we call it as equivalent capacitance. Equivalent capacitance will be basically adding of these capacitors together if they are parallel to each other. Okay, so now they will be series sometime. When they are series, what that means is this is connect into a single kind of wire. That is a single loop circuit that we're going to discuss later. But charges of this each capacitor is the same, right? So that means they have the same charges, but they may have different voltage. This voltage is divided into 3 parts in here according to the capacitance value. So now in this case, we call it as they connected serially. So now when they connect serial, your equivalent capacitance will be able to calculate by using this formula when they are series to each other. Okay. Okay, so now last part is RC circuit. RC circuit means resistor is R, C is the capacitor. RC together we call it as the charging and discharging capacitors. So I want to discuss this in this section because I will not come back to this later on, and you have one experiment that you're going to do in the laboratory related to the charging and discharging, because I think it is most important experiment, although that is not going to cover mostly in your class, but this is where that I'm going to cover that part. So now, what is the charging and discharging means? Charging means you store the energy. Discharging means you're using the energy. Similar to that, you charge your computer and you're going to use it without the power. Something like that, right? So now you can connect it to a single circuit. So now we'll say I have a capacitor. And then I'm going to connect that capacitor to the power supply by connecting here. You see that here? By connection this to the power supply, and I have a resistor. We'll say in this case light bulb. I have a light bulb, right? So now when I connect the circuit, I definitely know some charges will pump from the power supply and go through the circuit, and this is going to be charge. That is called it as charging, right? And what happened to the light bulb? Light bulb going to be lighted up. Sometime you're going to see it will dim and then light will be disappeared after some time. Why is that? Because your capacitor is fully charged, then there is no current passes through the capacitor because it is fully charged. Then your light going to be disappeared. So now discharging means you don't want the power supply, you disconnect power supply and you're going to directly connect this into your left circuit on, right circuit only. So now when I do that, what will happen is I am using my charge capacitor to light it up my light bulb. So now charge particle go through the loop and this going to again light it up. So after some time, again, light going to be dim and disappeared because that's the ending of the charges that I stored in the capacitor. That is the process that we call it as charging and discharging. Okay, so now how graphs looks like. So now if I plot the voltage as a function of time for the charging process, you're going to see this kind of plot. So let's analyze this. So now in charging, capacitors means is changing with the time. So voltage changing with the time will follow the charging behavior of this curve. Time T is the time, epsilon is the voltage of the battery, and then I have T times R and C. R is the resistance, C is the capacitance. Okay, so now if you plot this and if you take the 0.63 times your voltage of the battery, and if you take the time at that point, we call that as the time constant. This is called it as the time constant. Time constant is equal to R and C, basically. Why is that? Because if you use in here, this part in here, if you use T equal R and C, what will happen is exponential minus RC over RC will be just exponential minus 1. that value will be around 0.37. So then you will see 1 minus 0.37 will reach this number. Okay, when time equal R and C. So purpose of charging and discharging capacitor is you can easily calculate the unknown capacitance of the capacitor that you're going to do it on the experiment. And similarly, charge behave the same and current behave exponential also. Not the same behavior, but a little different behavior. So now discharging has the different formula. Discharging will work this way. So your voltage start with the voltage of the battery and then it's going to getting lower and lower. But when you have 0.37 of the voltage of the battery, you're going to reach your time constant. Okay, that is for the discharging. Okay, so that will be for the RC circuit. That's it for this chapter. It is a long chapter, but we're going to do some presentation worksheet related to the materials that you learn, and you're going to do the experiment as usual related to the capacitors and also equipotentials in your as your first experiment.